to the webinar session, Introduction to Functional Safety for High Voltage Systems. My name is Martin Stäbler. I'm a system engineer in TI's Industrial Motor Drive System team. In the next 45 minutes, my colleague, Ashish Manjari, who's a system engineer for C2000 MCUs, and I will cover industrial and automotive functional safety examples in high voltage systems. After an introduction and overview on functional safety standards, we will go over safe off concepts with industrial electric drive. Following that, we will look into safe motion concepts and how C2000 MCUs support this. We will then look into safe automotive traction inverters before we conclude this session. Why safety matters in high voltage applications? On the left, we can see 3 examples applications. When we refer to high voltage from a semiconductor view, we mean AC grid voltage less than 1000 volt RMS or equivalent DC voltages such as 800 volt DC as used with an electric car traction inverter. For all these applications, such as variable speed drive, traction inverters, or solar inverters, electrical isolation is key for every product to protect humans from an electric shock. On the other hand, there are many more serious hazards with high voltage, high power applications, such as an industrial robot. For example, as shown on the left-hand side, what if the robot moves unintended? It could then seriously injure the operator. Functional safety is key for overall risk reduction of all of these hazards to an acceptable risk. Let's have a look at a simplified block diagram of an AC input servo drive. The AC-DC rectifier and the DC-AC frequency inverter carry high voltage. To protect humans from these high voltages and an electric shock, this section is typically reinforced isolated to the human-machine interface. The HMI only exhibits voltages less than a 60 volt DC, therefore. For electrical safety, industrial drives need to comply to the corresponding electrical safety standards, as shown on the left, the IEC 61800-5-1 safety requirements, electrical, thermal, and energy. Since the isolation is typically realized with reinforced isolated gate drivers and current sensors, these semiconductors need to comply to relevant electrical safety standards too. For capacitive and magnetic isolation-based semiconductors, the IEC 6747-17 and the VDE 0884-17 are the relevant standards, and TI isolators comply to these standards. Now, what does it take to make this a functional safety-enabled drive? Let's have a look at a few key standards for industrial machinery and electric drive. There are 2 concurrent standards for industrial machinery, where electric drives are a key part. The ISO 13849 specifies safety of machinery for the control system, and the risk reduction of hazards is expressed as performance levels. The IEC 6261 and the IEC 61800-5-2 specify functional safety for industrial machinery and variable speed drives, and here risk reduction is expressed as safety intensity level SIL. Both standards refer to the key safety standard IEC 61508 for electronic safety-related systems. There are predefined safety functions, and a few examples are listed on the table on the right. Safe torque off, STO, for example, prevents force-producing power from being provided to the motor. STO is an uncontrolled stop in accordance with stop category 0 of the industrial machinery standard. Another safety function, for example, is the safely limited speed, SLS. This function reduces the speed of the drive to a tolerable value to prevent from a hazard. What about the safe subsystem architecture? The ISO 13849 industrial machinery standard specifies the safety architecture. For example, category 2 demands a single channel system with monitoring. This system has a hardware fault tolerance of 0. The block diagram is shown on the left. Higher performance level, or the highest performance level E, requires either category 3 or category 4 at a minimum, which are dual channel systems with cross monitoring and a hardware fault tolerance of 1. So these systems can tolerate a single fault while still being able to execute the safety function. On the other hand, if we look at the IEC standard, in that case the IEC 61800-5-2, it does not demand a specific hardware fault tolerance as long as the desired safety integrity level is met. Let's take an example. For example, SIL 3 is equivalent to the ISO 13849 performance level E. And as shown before on the figure on the right, this level requires minimum category 3. Hence, this is a dual channel system with a hardware fault tolerance of 1. Therefore, we typically see that safe drives are often certified against both standards, and we see dual channel systems with a hardware fault tolerance of 1 in industrial. What about automotive, Ashish?
Yes, Martin. In principle, the automotive functional safety standard, that is ISO 126262, is an adaptation of IEC 61508 and tuned for the automotive use cases. Hence, there are similarities in the processes and architectures required for functional safety in both the standards, and yet there are differences. As shown in the figure on the left side, ISO 26262 provides V model as a reference for product development and the automotive-specific risk-based approach for SE determination. SE stands for Automotive Safety Integrity Level, similar to the IEC 61508, SIL, SIL, or ISO 13849, PL, that is performance levels. ISO 26262 provides guidelines across all the life cycle phases in relevant for the automotive, starting from the part 2, that is management of the functional safety, to the concept phase and the product development at the system level covered in the part 3 and part 4, followed by the product development at hardware and software levels are covered in the part 5 and part 6. Part 7 covers production, operation, and there are also guidelines in the standard till the decommissioning of the product. Let us look at what the requirements drive in the automotive functional safety architectures. There are key differences that we need to understand between the industrial and automotive use cases for the functional safety. In an industrial system, the safety function is typically applied to an equipment under control, or EUC, that is clearly identifiable and separable from the safety functions. This distinction between the safety function and the intended function is not always possible in case of automotive. For example, traction inverter system in the electric vehicles is also implementing the safe torque functions for an electric vehicle. The safety function is tightly integrated with the intended function. Now, apart from the severity, exposure, the risk assessment in automotive takes into account the controllability of the situation by the driver. This is not considered in the industrial systems for the risk assessment. Industrial systems are typically low volume and automotive systems tend to be mass-produced. This adds additional care about in the automotive development that is typically spread across multiple organizations, and the relations between the customers and suppliers could have an impact on the overall safety implications. Typical system safety architecture for higher functional safety is 1 out of 1002 for the industrial systems, which means HFT equal to 1, and the same in case of automotive is 1 out of 1D. 1 out of 1D is a single channel HFT equal to 0 architecture that is typically seen in today's automotive systems. Martin, let's look at the various safe torque of schemes possible in the industrial systems.
Thank you, Ashish. So let's have a look at option to realize safe torque off, or on the other hand, disable torque generating power to the motor. With mechanical relays, this can be achieved by either disconnect the AC mains input to the inverter, or we can disconnect the output of the inverter to the motor. Today's drives, however, typically use electronic solutions, as shown with items number 3, 4, and 5. For example, we can remove the power supply from the gate driver, or we can disable the PWM input to the gate driver, so the power switch will turn off and no power will be generated to the motor. MCU-based solutions also allow set the torque command to 0. Electronic solutions typically allow faster response time to STO as well as faster recovery from STO, and are also typically more reliable versus mechanical solutions. Let's have a look at the subsystem of an STO dual-channel system. The table shows typical architecture to cut off power supply or PWM input to the gate driver. The architecture 1 on the left. Channel A, or channel 1, cuts off power from the anode of the 3 topside gate drivers. Channel B, or channel 2, cuts off power from the anode of the 3 bottom side gate drivers. This topology is, for example, shown as an example in the variable speed drive functional safety standard in Annex B. It also typically only requires 5 volt or 3.3 volt load switches. The architecture 2 in the middle, we have channel B, which cuts off the power to the anode or the logic supply, in case of CMOS gate driver, of all 6 gate drivers. The second channel, channel A, cuts off the isolated supply of the secondary side of all 6 gate drivers. This approach might be very suitable for multi-channel digital isolators or half-bridge gate drivers. Architecture 3 has 2 redundant switches in series and cuts off power to the isolated supply of the secondary side of all 6 gate drivers. In that case, it typically requires 2 24-volt rated load switches. On the other hand, it may be easier to retrofit to an existing non-safe drive. The architecture 4 example does not cut power, but turns the PWM off through a fast AND gate. It requires very short periodic diagnostic test pulses to validate the STO function can still disable the output of the buffer independent of the non-safe PWM signal. The RC filter at the output of the buffer will remove these short test pulses to ensure the gate driver doesn't turn on or off during the operation, and the propagation delay of that RC filter will contribute to the overall PWM propagation delay. So this needs to be considered in the system design. Let's have a look at an example reference design from Texas Instruments. The block diagram shows a two-facet STO concept which cuts off power on the logic supply of the 6 CMOS input gate drivers, as well it cuts off power of the isolated supply on the secondary side on the 6 gate drivers. The channel 1, or in that case STO1 in yellow, as shown, cuts off the power supply of the logic side, ECC, and the channel number 2 cuts off the power supply to the isolated DC-DC gate drive supply, therefore cutting off the isolated 6 supply rails to the gate driver. The diagnostic in that case is run on a still 1 rated MCU, and we also have a STO feedback to the programmable logic controller. Where to get information on this design? This design is supported with a TÜV report, a safety manual, and a qualitative system FMEA, and these documents are available on TI.com on the corresponding TI design folder. Let's have a closer look into the STO1 load switch subsystem. We can see here we have a 20-volt STO input. So we have an input receiver, isolated input receiver, which then turns off the load switch in case of an STO. And this load switch removes power from our CMOS input isolated gate driver. What about failure modes of these semiconductors? Where do we get this information on failure modes? Failure modes can be found in the relevant industrial and automotive standards as listed on this slide. Or, for example, also in handbooks from Exida. Now, since we want to certify also against the industrial machinery standard ISO 13849, what about failure modes for capacitive isolators? The ISO 13849-2 from 2012 does only mention optical isolators. Well, we go to one of the other safety standards. In that case, we go to the IEC 61800-5-2 for variable speed drives. If we refer to the table D5, we see signal isolation components. So the IEC is generic on isolation and does not specify the type of isolation, whether it's optical, magnetic, or capacitive anymore. Now let's have a look at the most important criterion, the fault exclusion. We want to exclude a fault which is a short across the isolation. This can be excluded if 2 items are met. The signal isolation component, the isolation, needs to be built in accordance to the overvoltage category 3, according to the IEC 61000-5-2. Second requirement is that measures have to be taken to ensure internal failure of the signal isolation component cannot result in excessive temperature of its isolation material. Let's see how TI's isolators meet these requirements. We'll have a look at our reinforced isolated gate driver UCC 21750. In the isolation specification on the left, we can see that it's rated over voltage category 3 up to 1000 volt RMS, and therefore meets the requirement on the table D5 shown on the slide before. What about excessive temperatures? Safety limiting values as specified in the datasheet. Here, the example from the UCC 217 datasheet. We see maximum current and maximum power. They intend to minimize potential damage to the isolation barrier upon failure of the input or output circuitry. A failure of the I/O can allow low resistance to ground or supply and, without current limiting, dissipate sufficient power to overheat the die and may damage the isolation barrier. To prevent this, a possible system solution can use an LDO with a current limit, or it can use current limit resistors, as shown on the right-hand figure. For more information, refer to the application note, Understanding Failure Modes in Isolator. What about the component FMEA? Let's have a look at a load switch example, which cuts power to the gate driver. The diagnostic, as shown here, periodically turns off the load switch very shortly and then monitor for faults, such as a switch remains stuck on. To do the component FMEA, TI provide additional information for functional safety, such as for analog ICs, such as fit rates for the TR 62380 and ISO 26262 port 11, and also the Siemens norm. We also provide failure mode and failure mode distribution, as shown in the table 3.1 below. Now let's do a quick example how we calculate the safe failure fraction from these failure modes shown below. So we go through the failure modes, and we can probably start on the first one. If the output is open or high Z, this is a safe failure. If we continue, we will see there are dangerous failures, but these are detected. We finally come to pin short. This can be any pin, any of two pins. Here in this example, we assume 50% are safe failures, and the diagnostic identifies 90% of the remaining 50% dangerous failures. If we now do the math, we can get a safe failure fraction, in that case, of 99.75%. Along with the fit rate provided in the document 2, the probability of dangerous failures on demand per hour can be calculated too for this IC. This process needs to be continued for all components of the safe subsystem, of course. Now, we get our safety-enabled industrial drive with safe torque off support. In that case, we should show a dual-channel system, STOA and STOB. To add safe motion functions, like safe limited speed, safe limited torque, or safe stop 2, it typically requires safety MCUs. And a typical approach are extended safety modules with dual MCUs which cross-monitor each other. In case of a fault, one of the safety MCUs, the system will trigger STO to get into a safe state. What about other safety MCU architecture? Let's start with the topology shown on the previous slide and shown in the left column. A key advantage of separate safety MCUs is that the hardware is scalable and firmware updates are separate for the safety MCUs and the control and communication MCU. The system can therefore be offered without safety, hence no overhead for the safety, and the safety module would only be added when safety is required. To save BOM and space, one of the safety channels can be integrated into the control MCU, which now becomes a safety MCU2, as shown in the middle column. We have two assessed concepts based on C2000 MCU for both of use cases. The third architecture on the right now moves both safety channels into the communication and control MCU respectively. For systems like industrial robots, which typically always require functional safety, it offers a further path to BOM cost and space reduction. What safety features and diagnostic coverage do C2000 MCUs have, Ashish?
Right. So in C2000, we build a real-time controller that are optimized for power efficiency and density in mind. Based on the unique and innovative feature set and years of power control system expertise that we have developed will help you to design your systems faster. The support from the microcontroller for the functional safety includes the hardware architecture that has been tuned for functional safety applications, supported by the software libraries, and importantly, the functional safety collateral. This can help you in certifying your systems faster. We will take a look at all these in the next slides. Typical safety function implementation consists of 3 steps: sensing, processing, and actuation. In some cases, additional function of communication with the external component is required. For the safety of sensing, C2000 MCUs support the redundant and diverse sensing peripherals, such as ADC and the comparator subsystem CMPSs. The built-in hardware sensor data processing and automatic result comparison in the hardware is implemented for the microcontroller. This saves significant overhead of processing the same, and it saves the software development time as well. Extensive interconnection between the sensors and actuators via the on-chip crossbar architecture can activate the safe state even independent of the CPU. For the safety of processing, the microcontroller architecture with redundant cores is optimized for both automotive as well as industrial safety systems. For automotive use cases, the dual-core lockstep architecture provides comprehensive coverage of the faults within the processing unit. In multi-core devices, the C2ATX and the CLA cores offers diverse architectures for implementing the effective reciprocal comparison with high confidence and the reduced system development time. In addition, the periodic testing of the CPU core in the long-running industrial environment is supported by online hardware-based. This helps in avoiding accumulation of faults that is a key requirement for the ISO 13849 PLE, which is an HFT equal to 1 and dual-channel system architecture. The actuation safety is supported by the redundant peripherals with on-chip CLB, that is configurable logic block, and other modules that can be used as a smart comparator without causing spurious trips or false alarms in the system. To support the safe communication, the microcontroller has built-in hardware features, including the memory ECC and parity, and software test libraries for the core. The microcontroller can support multiple safety functions, and possibly with different safety integrity levels for each one of them. And they need to coexist on the same microcontroller. So the MCU supports features in the hardware which will help keeping the isolation between the various safety functions with the built-in hardware features. More details on the device safety concept can be found in the individual devices safety manual. More details on the functional safety capabilities of each C2000 MCU, the collateral that is supported with those MCUs, and the additional information about the software libraries, etc. can be found on the ti.com. Here is the link. One of the key collateral offered for the microcontroller, which is customizable FMEDA. This can be tuned for the end use cases and variety of safety concepts. This is what a typical C2000 MCU FMEDA looks like. It is organized in multiple tabs in the spreadsheet. As you may have already noticed, each tab has a distinct color, mainly blue and the green. Blue color tabs are the fields inside the FMEDA where your input can be customized by the system integrator. The green color tabs are the place where the results or the outputs of the FMEDA customization are reflected. Blue color tabs have fields which values can be entered by the user. The default values of these fields can be changed based on the needs of the user application. The green tabs show the result of computation based on the choices made in the blue tabs. The blue tabs allow the user to enter the custom values as per the end application. The safety function that includes the fit estimation tab, the product function tailoring tab, the safety mechanism tailoring tab, pin level tailoring, and finally the custom diagnostics. The green color tabs, which gives users access to the results, are classified mainly as summary and detailed. The Results tab shows the results for both the standards, ISO 26262 and IEC 61508. The underlying data used in producing both the results is coherent, and the computation done is as required for the respective standards requirement. We will see some more examples of the customization allowed in the blue tabs in the next slide. Let's see a few examples here where the FMEDA customization is required by the end user. Change in the technical safety requirement or safety concept at the application level. The microcontroller is considered to be designed as safety element out of context, that is SEOOC. And these component FMEDA are created based on assumptions of functional safety requirements. Hardware safety requirements at the microcontroller level for each part and subpart are satisfied by implementing safety mechanisms that are described in the safety manual. This will meet the allocated safety integrity level for the microcontroller. For example, here, the reciprocal comparison by software is default associated with the CPU, single point faults, and is claimed to have 90% diagnostic coverage. When there is a change in the application level safety requirements, it drives the updates required in the allocated to the microcontroller. Additional safety mechanisms may be required to be defined to meet the new goal. The new safety mechanism will be required to be associated and the failure modes of to the respective CPU parts of the MCU. The effect of this action needs to be verified by recomputing the hardware matrix at the part level and also at the MCU level. Here is an example where the original safety target allocated to the CPU of SLB as in boy is changed to SLD at the application level. The existing safety mechanism with the original diagnostic coverage associated with the failure mode of the CPU may not be adequate. Hence, customer can add an additional custom safety mechanism with appropriate justification, can justify the higher diagnostic coverage implemented at the system level safety mechanism, which is 99%, and can implement the change in the safety requirement for an application. Change in the device resources used in the safety function. The default usage of on-chip resources in FMEDA calculation is assumed to be 100% of the available ones. In reality, the application may not utilize all the peripherals and all the memories available on the device, which is safety related. Often, there is a need to tune the resources applicable as for the end use case. Note that the selection or deselection of certain resources may have significant impact on the base failure rate calculation. Tuning this FMEDA for the exact use cases become an important step at the beginning of safety analysis at the application level. Let's look at another customization of the FMEDA, which is devices use environment, which is different than the default. This is a typical example of customization required in the FMEDA in the beginning phase, where there is a change in the operating mission profile. Selection of appropriate packaging type, maximum power dissipated, related to the microcontroller and the application is an important step as it impacts the base failure rate calculation. Default setting for the out-of-the-box FMEDA may not be accurately representing your use case. Hence, this customization becomes a necessary step in the beginning of your safety analysis. Now let's look at an example of the system safety concept involving the microcontroller, which is assessed by the third-party assessor ToolSoul. This is supported as a part of the C2000MC collateral and available for customers on request. This is an example of an easy reference system. The powertrain consists of three modules, mainly the onboard charger, which includes AC-DC and high voltage DC-DC. The high voltage DC-DC converts the 400 volt to 48 or 12 volt, providing the powerful support to the body control modules like electrical power steering and infotainment systems. The third one is a traction inverter for the traction motor drives. From a technical challenge point of view, given the fact that most of the power electronic engineers are from analog based, while moving to the digital design world, our reference design solutions play a critical role to get them started. Along with the hardware reference design, the guidance for achieving the safety certification of the same system is an important topic. This guidance of using C2000 MCU and certifying your system is provided with the safety concept document as a part of the safety package for this microcontroller. We have seen ISO 26262V model of product development earlier. The part 3 covers the concept phase. This is the step that is expected to be done by the system integrator. This starts with the hazard analysis and risk assessment and results into the determination of risk levels and, more importantly, the safety goals. The functional safety and the technical safety requirements are derived from each safety goal. And the safety requirements are then allocated to the hardware and software components. TI's reference design with the functional safety concept assessed by TUSU provides guidance to perform this analysis at the system level. This includes the concept FMEA, DFA, and coexistence analysis, and finally, the system integrator responsibilities. This helps to improve the time to market for the system integrators. As part of the safety package available for customers on request, it includes the main safety concept document on the top left. This explains the safety goals, assumptions of the system block diagram, and followed by the detailed analysis at the system safety function implementation. The safety assessment report from the independent third-party assessor is also included in this package. In a high voltage system involving the microcontroller, the gate driver IC is a critical component to achieve the functional safety of the system. TI supports gate driver IC that are AEC Q100 qualified and can support system design up to the highest level of the safety integrity, that is ACD. The gate driver IC supports integrated diagnostics and advanced protection features to help achieve system-level safety function implementation without overhead in the system development. This includes built-in self-test for the protection comparators, communication data integrity check for the isolation, internal clock monitoring, and fault alarm and warning outputs for the communication of the fault detection. And the protection features includes the overcurrent protection with 75 nanosecond response time, support for the active short circuit protection ASC, supply undervoltage and overvoltage protection, and active output pull down and the default low outputs. There are many features included with the gate drivers that can be found in the device's safety manual. TI's functional safety product development is certified according to ISO 26262 and IEC 61508. The product classification as functional safety capable, functional safety quality managed, and functional safety compliant helps customers choosing the right products for their right applications. FMEDA, FMA, safety manual, and safety certification documentation, along with the system safety concept assessment reports, are available to the customers on the request. Thus, so far in this presentation today, we have seen the high voltage technologies are necessary to provide energy efficiencies and are key to our sustainable future. When it comes to safer human interface with the high voltage systems, semiconductor solutions are necessary. Industrial and automotive functional safety requirements have similarities and differences. There are TI products and support tools enabled to both the type of applications in industrial and automotive to accelerate your time to market. And this support includes the compliant or the hardware certified products that implements the differentiated features in the hardware for functional safety, the system level safety concept collateral, and support for the software libraries. With this, Martin and I would like to thank you for attending the webinar and look forward to your questions now.